Welcome to my YouTube channel Erudispace. I am Dr. Mohanty, and today we'll discuss about the turbojet engine. So before discussing the turbojet engine, we should know that the turbojet engine is the most widely used jet engine. And jet propulsion cycle is similar to your Brayton cycle, but not exactly the same. And before that, you should understand what is the principle of jet propulsion. Jet propulsion is on the basis of Newton's third law. So what is Newton's third law? According to Newton's third law, every action has an equal and opposite reaction. So when a very high stream of gas leaves one end, a thrust is produced just in the opposite direction. On that principle, all the jet engines actually work. So first we will consider the turbojet engine. And before discussing the turbojet engine, let me briefly tell you what happens in case of your simple open gas turbine cycle. The simple open gas turbine cycle consists of three essential components. They are your compression, your combustion chamber, and then your turbine. This actually represents your compression. Then you have the combustion chamber, and then you have the turbine. In the combustion chamber, heat and fuel are added. This one is your compression. This one is your turbine. They are in. This is your gas. So first, air is taken into the compression when it is compressed. Due to compression, its pressure and temperature is significantly raised. Then it is taken to the combustion chamber, where heat and fuel are added. Due to this huge amount of pressure and thermal energy is developed, it is taken to the turbine, where it develops power output. And this compression actually gets derived from the turbine. The same thing has been discussed in PV and DS diagram. The different thermodynamic processes are isentropic compression, then followed by constant pressure heat addition, followed by isentropic expansion, followed by constant pressure heat rejection. In fact, in open cycle gas turbine, it is exhausted. So exhaust can be considered equivalent to that of heat rejection. The same thing has been shown in TS diagram. Now, what happens in case of a turbojet engine? Does turbojet engine follow the same way in which actually the gas turbine cycle works? There are certain fundamental differences which separates the turbojet engine from the gas turbine. In case of your turbojet engine, the compression process is carried out in two components. They are your diffusion and your compression. Similarly, the expansion is carried out in turbine and nozzle. So let me draw the schematic diagram of the turbojet engine so that you can understand the actual operation. one is your diffuser. This one is your compression. This one is your combustion chamber. This one is your turbine, and this one is your nozzle. They are in and gas out. These are actually your fuels, and this one is the sound. So first of all, air is taken in to the diffuser, and diffuser is a smoothly varying section where the kinetic energy is converted into pressure energy. After that, it is taken to the compression, and in the mechanical compression, the pressure is significantly raised. Then it is taken to the combustion chamber. In the combustion chamber, heat and fuel are added to the compressed air, and due to this, huge amount of thermal and pressure energy is developed. Then it is taken to the turbine, where it undergoes expansion, and the power that is developed due to expansion in the turbine is actually utilized to meet the requirement of the compression and other auxiliary components. After that, it is taken to the nozzle. The nozzle actually is a smoothly varying section which converts the pressure energy into kinetic energy. So, the gas leaves with a very high velocity. I have already told you while discussing the principal object propulsion that it works on Newton's third law of motion. And according to Newton's third law of motion, every action has an equal and opposite reaction. So a jet of gas leaves the nozzle with a very high velocity, as a result of which a thrust is developed just in the opposite direction. So it moves the turbojet just in the opposite direction, and gas comes out in this direction, and the thrust is developed just in the opposite direction. And here the entry condition is taken as 0, entry condition to the diffuser, exit condition is 1, entry condition to the compressor is 1, exit condition is 2 as far as compressor is concerned. Similarly about combustion chamber, turbine and nozzle. Now actually we will discuss this with the help of a PV and PS diagram, and then we can compare how it differs from the simple open cycle gas turbine. First we will consider the PV diagram, and then we will consider the PS diagram. So let me first consider the PV diagram. This one is the PV diagram. So 0 to 1, that represents what is happening in the diffuser. That is nothing but your ramped compression. Then 1 to 2, that is taking place in the compression. 2 to 3 is taking place in the combustion chamber. 3 to 4 is what is taking place in the turbine. This one is taking place in the nozzle. This is your exhaust, which can be considered to be your heat rejection process. Now another thing that I would like to add, that even after passing through the combustion chamber, some amount of unburned fuel is left out. So for that we may provide a sort of afterburner. Afterburner solves the same purpose as that of the reheater, but it is not exactly the same as the reheater. The same has not been shown in PV diagram nor in the schematic diagram also. But afterburner do play its part when it comes to your turbojet engine. Then we will consider the TS diagram. Zero, 1, 2, 3, 4, 5. You may denote this as 1 dash, 2 dash, 4 dash and 5 dash. 0, 1 actually represents the actual compression that is taking place in the diffuser. 1 to 2 represents the actual compression that is taking place in the compression. 2 to 3 represents the heat addition in the combustion chamber. 3 to 4 represents the expansion that is taking place in the turbine, and 4 to 5 represents the expansion that is taking place in the nozzle. 0, 1 dash is actually an isentropic, an ideal process. 1, 2 dash is an ideal process. This is related to the diffuser, this is related to the compression. Similarly, we have 3, 4 dash, which is an ideal or isentropic process when it comes to your turbine, and 4, 5 dash represents the ideal or isentropic expansion taking place in the nozzle. Another thing that you have to bear it in mind, that when we are considering the turbojet engine, we consider that there is no pressure drop in the combustion chamber. In actual case, pressure drop may take place, but we assume the pressure drop to be negligibly small. And apart from that, the specific heat is assumed to be constant, that it doesn't vary over the range of temperatures. That is something that is assumed. Now, another important thing that you need to know, that you can have efficiencies of different components, like efficiency of diffuser, efficiency of the compression, efficiency of the turbine, and efficiency of the nozzle. While discussing the effect of irreversibilities on gas turbine cycle, I have discussed in details about the isentropic efficiencies of the compression and the turbine. We will follow the same principle in deriving the isentropic efficiency and efficiency of the diffuser as well as the compression. Similarly, while considering the turbine and the nozzle, we will adopt the same principle that has been adopted in deriving the isentropic efficiency of a turbine when it comes to simple open cycle gas turbine. Just let me give a simple example, other things you can yourself do. Suppose you have to find out the efficiency of the compression. So here it will be the ratio of the ideal isentropic enthalpy change to the actual one. Similarly, if you have to find out for turbine, it is just the reverse. So you can easily find out the isentropic efficiency of the diffuser, the compressor, the turbine, as well as that of nozzle. If you have to find out the efficiency of the cycle, you can adopt again the first principle to find out the efficiency, considering the net work output that you get divided by liquid supplied. Already those things have been discussed in details, so I don't want to take much of your time in deriving the efficiency that you can do without any practical difficulty. Then as far as the compression is concerned, usually we go for centrifugal or axial flow compressions. Both have their own advantages and disadvantages. The centrifugal compressors are used because they are quite convenient to repair and they are also durable. But as far as the performance is concerned, the axial flow compressors are more efficient, and apart from that, they are comparatively slim compared to the centrifugal compressions. And what are the advantages of this turbojet engine over other reciprocating engines? That here the ratio of power to weight is very high and the lubrication is also very effective and is not at all complicated. But when it comes to its performance at low speed, it is not at all something that is encouraging. And apart from that, it does have starting problems also. But in spite of its limitations, it finds extensive application in jet engines, and one of the most widely used jet engine is your turbojet engine. Of course, turbofan engine is also being used in a number of applications, but turbojet engine has got a very wider application. So I sincerely believe that today's lecture on turbojet engine would be extremely useful for all of you. We have discussed in detail the operation of a turbojet engine with a schematic diagram, and apart from that, we have compared this with simple open cycle gas turbine. If you have any doubt, please do put questions so that I will try to answer. Hope to see you soon for another lecture on my YouTube channel, Erudispace.